I have the generic title for the course, Machine Learning for Geophysics. But yeah, today is going to be mostly about processing seismic data, which is no doubt important in the context of geophysics. Yeah, so I've been already introduced. I will just move forward with the discussion. So, yeah, so it is not surpriseful. I mean, all of us that machine learning is playing a massive transformational impact in general in many applications. All of them have some subject matter expertise involved. If you work with people in pharma, there is expertise in pharmaceutical industry. But if you work with people in geophysics, then there is the subject matter expertise in geophysics. So you need both of them. You need the tools and you need that subject matter expertise. My role is to help you with these cutting edge tools, especially to the people in geophysics. Although I will talk also about the problem that we are solving in the context of geophysics, but my role is to emphasize the machine learning component of it. So in the artificial intelligence, not surprisingly, is in 2022 playing a role in the market of about $500 billion in 2022, growing to about 5 times that in 2032. That's about a 20% rate of growth, and that is a projection, but is it shows how much is making an impact. Another area that is strongly related is natural language processing. We have, in fact, seen how these tools like ChatGPT and so on came to the market and started basically change the way we search, change the way we think about topics. It's great for brainstorming. If you haven't used them, it's good for brainstorming. It's not always accurate, but it can give you good ideas sometimes. So natural language processing also growing at a rate of about 23%. Now in geophysics, due to the fact that, I mean, certainly there is an expertise that is not always easy to mix with this another field of machine learning. The penetration of AI has been a bit slower, but is catching up. So we have in an estimation here from an agency of about 13% growth in software service market. And these are just estimates. They don't need to be accurate. But also I have seen many geophysicists now actually coding in Python and solving some of these problems. I work with some of them. You can see how the number of papers, in fact, in Society of Exploration Geophysics has been growing massively. For example, here almost doubling from 2009 to 2020, and this trend has continued. Definitely, this graph is not up to date, but it's a trend that is still going on. You can see how we have almost 3 times here in the American Geophysics Union, and yeah, definitely the growth is exponential, and a reason to pay attention to what is happening. Now let's talk about the problem briefly. We're not going to go into too many details, but and I know many of you have background in geophysics, so I don't want to go too deep into this description, but I want to give the basics for those who don't have that background. So the way seismic data works is that you generate a vibration. That vibration is reflected whenever there is transitions in the layers in the subsurface, and that's recorded. The reflections are recorded, and they give you information about the presence of oil, gas, and other resources in the subsurface. So yeah, like thickness, structural features of the underground rock formations, and so on. And it's important to have also a good idea of how the geometric configuration works. So generally you have a source. That source will emit these vibrations. They will be reflected and captured at the receivers. Those receivers, I mean, the delays of that travel time and the reflection give you information about the depth, about the composition, and so on. And yeah, so the receivers are aligned in a configuration that is parallel to the relative position between the source and the receiver. So you can see here a picture of how they are arranged. And then you have the source is now going to move, generating wave at different distances from the receivers. That generates this geometric configuration. You have the source moving in. So this is called the cross-line direction, and this is called the inline direction. This is a convention, and it's used frequently whenever we are talking about seismic data. Now, thanks for those people who don't have access to this data, especially, and to seismic data, and probably you don't have, I mean, for those people who don't have access to that data, don't have access to data that has been labeled by those experts who do the analysis of the data, then you have some heroes who have created data like the Netherlands data sets, which is nice for testing algorithms and so on. Yeah, this particular one is a 384 kilometers square in the Dutch offshore portion of the central Garbe Basin. Is available open source to everyone. It has 651 inlines and 951 cross lines, and the labels for the different horizons, basically the separation of the layers of the subsurface have been already generated. That means we have the expertise from those people who actually separate that, do that analysis, and that could be used to train machine learning algorithms. So let's look a bit more into that. So this is the Netherlands datasets. They have nine horizons here. And those here is an example in line section, as this is the time direction basically. Time because as the wave is reflected, so there is a time that reflects the depth indirectly. And also there is information about the materials. But, and you can see here the labels corresponding to the horizons, to the different phases of the subsurface. And this is great because, I mean, without trying to go further into machine learning and the tools and so on, you can imagine, is it possible really to train a machine learning model to separate these components of the subsurface and to do what the experts have done here? And is it good enough? Because here we're basically separating kind of textural information and other characteristics that are more human-like observations rather than, if you think about a generic image, it's generally made of pixels. That pixels is just numeric representation, and that's what the computer sees. Here, it is actually a signal, so it's not exactly pixels, but again, the way it's labeled is by observations by a human, and then these machine learning models have to think more like a human to do this kind of separations of horizons. So the seismic interpretation is basically that process of separating components or observations within that subsurface is quite a challenge. And yeah, it involves analyzing patterns, shapes, characteristics of seismic reflections to infer subsurface structures, stratigraphy, and lithology. Now, it is a time-consuming task, requires a lot of expertise from humans, it takes time, data is generally noisy, and this is quite an interesting challenge, it's noisy and limited in spatial and temporal resolution, usually requires weeks or months to do this analysis of identifying all these structural components within the subsurface. Now, yeah, thanks to the fact that we have now a deep learning, which is that ability to kind of interpret this image in a way that is more human-like, then we may be able to use these great tools to do the separation. In fact, there's people already doing that, but there is also research. So I don't think anyone has the final answer to this yet, but there is some there's great big progress. Some of it already implemented in softwares. Some of it hasn't. I know people who do research in this area. Now, yeah, we now let's try to get into the context of machine learning and kind of relate back to the problem of seismic data and see how it really helps in the process. So in any process, wherever you have to apply machine learning, there will always be, I mean, there is a pre-process. You have to clean the data, normalization, we're not going to talk too much about that today, not today. But there is a very important part. Once you have the data like very nicely prepared for your algorithm, where you have, let's say, your image, your sections, your labels of the horizons and so on, you have to do what is define your validation strategy. And this is general statistics, and it applies to many areas, many fields. You do something based on some knowledge. You apply that for prediction on some area. You have that knowledge, that algorithm, or that equation has never seen before. And if it applies, then excellent. I mean, this is all physics. I mean, you simply developed a theory and then test that theory and make sure that it's generalizable. And machine learning is exactly about that. You build something based on a theory, you make sure that is generalizable to a data that has never seen that you have never seen before. but shows the same type of characteristics. So always you're going to split your data into something that is called the train, the validation, and the test set. And this is very important because I think many people who start doing machine learning, and they just have one single validation and test set as a single thing. You need the three. You need the three, and we're going to talk about why you need the three. So for usually to train your algorithm, not surprisingly, you will need to give them examples. And those examples is a trained data set. You will go through a validation, and you will go, and then you validate whatever algorithm or method or model you use to predict that data. And then you develop your model through testing many options, many models, many algorithms, many rules, whatever you want to test. You can create a new type of machine learning. I mean, if you have the time to explore, you can do so. But always you develop that first model, and that model is gonna give me the best metrics, the best accuracy, precision. We're gonna talk about the definition of those terms, but today, everyone have an idea what accuracy and precision means. Once you have the best you can with the algorithm that you develop, you have your first model. But those metrics, let's say it tells you it's 95% accurate. That has no value here. And that has no value because in your process of testing many options, many algorithms and so on, you slightly, and listen carefully, because slightly train also your algorithm on that second validation set. So this validation set is no longer going to give you a good metric. So at that next step, you join your train and validation sets, and you get a second model. So let's look at this picture. So this is a nice picture. You have your train. You use this to train your first model by trying many options and validating. Once you have decided the best way to do so, you join them to and train a second model. We talk about machine learning models, but it's just a lot of weights and parameters that you use in the prediction. So, and after you have done that combination, and created a second model, that is the model where you're going to get the metrics. But you have to remember one thing. At this stage, you will no longer try any other option. You finish trying all the algorithms that you could try here. And you test now and get the metrics on the test set. And this metric is usually gonna be slightly lower. You will see that because you slightly fitted, trying many things, your data to the validation. So this can go like 2% lower, your test set. In precision, in accuracy. So let's say you reach 92% with your validation set in this testing, then usually it's gonna go 90% when you test it on the test set. But this is I wouldn't say the real, but the most valuable, the most valuable metric that you obtain. And this is the one to report to whoever your boss, your manager is, or if it is yourself, if it's your own project, then you know this is the one that you should trust. This metric coming out of testing a model that has now been trained on both train and validation on the test set. Finally, if you're going to take this to some production, you're going to put this into a server, and that server is going to periodically do a process of prediction, or you're going to do it manually, it doesn't matter. You join the three data sets and you train a third model. Then you test it. You test on something else, on more real data that is outside. If you have something different, that way helps you see that the model is still making coherent predictions. This process is quite important because if I see someone who doesn't have the background in machine learning, they do this, doesn't have the background in data science, they do this wrong most of the time. And especially the not using the three components. So this is my critical test. I mean, when I see someone who is just learning without proper understanding of statistics, then I know they're gonna fail at this, and I know that. I see the code, I see that failure. So how can we probably split the data? Well, we can probably break this data, you see, along the inline direction or the cross-line direction, and take a set of examples from here as my train set, a subsequent set as my validation, and a subsequent set as my test set. It can go a bit, I mean, there is other things that you may consider in that splitting, but let's keep it as simple as that. Now, let's talk about something that is quite important in deep learning, in machine learning. So whenever you are processing images today, or images like data, so 2D data, you should be using deep learning. So, unlikely, unless the data is somehow is very simple, like you're just looking for a minima or a maxima or something like that, okay, you don't need deep learning. But when you're looking for information like texture, shapes, and this is the kind of things that you are looking for in this type of seismic data, you should be using deep learning. And the architecture that is generally used is the encoder-decoder architecture. It's also called the autoencoder, and it basically has one component that is going to encode my sections, my seismic sections, for example, is that's what I have as an input, and bring it down to data that is a lot smaller. It's called the bottleneck precisely because this data is quite small. And then there's something very interesting here, because this data here in the latent space has all the information to generate back the same image here and reconstructing the image. So technically means that I can just start with this section, bring it down to a few parameters in the latent space, and regenerate back from those few parameters with a smaller set of elements in a vector, regenerate back this image. What it means is that in this latent space, I have all the necessary information to understand the seismic but not necessarily just all the information to generate the pixels. It's more like a descriptive type of information. So if you have a good encoder and a good decoder, generally that involves enough, let's say, layers of processing. Let's call them layers. We're going to discuss that. That means if it is deep enough, generally they will begin to observe complex abstract features in the data. And those abstract features is information that you have here in the latent space. And that abstract features looks like, when you're observing these, then you can see, okay, here there seems to be larger fluctuations. Here they tend to be smooth. Here they are a bit fast, transition. So anything that you visually can describe about the texture somehow of these, more like a human-like abstract interpretation of it. That is no longer just looking at numeric values. That is the type of things that you ideally have in this latent space. A description of the image. In numerical representation, this is a vector. This is entirely a vector. And yeah, so the encoder basically contracts that information into a description in terms of features of that original image. And then the decoder uses that small information, that latent space, and reconstruct back the image. Yeah, so here it is. The latent space contains the knowledge representation of the original input image. And this is quite important. You're going to see these all across AI, machine learning, and in deep learning, even transforms, like if you think OpenAI, ChatGPT, they all use the decoder architecture. If you think about any AI processing tool that has been developed, most likely, like almost entirely uses the encoder-decoder. There is exception. Usually, once you have trained also, sometimes they only take the encoder. We're going to talk about that. And sometimes there is only one famous case where they decided to take the decoder only. And that's kind of funny. But not for today. That's the GPT guys. Now, one layer that is often implemented for processing. So we look into all these layers, which are the processing layers. So you have your original image. It's going to go through a series of processing layers. And one common layer is the dense layer. This layer takes all your input data. That means your image and it's going to apply some weights, multiply all these input parameters all across the image to generate, some product vector there, input plus a kernel is a matrix, and a bias that is a vector here that is added to the product between the input and these kernels. And then there is a nonlinear activation layer. Now, the parameters of this matrix are going to be learned in the process of training that machine learning model. And the same as the bias tend to evolve in your training process until it leads to an output that is consistent with the prediction that I am expected at the very end of the process. Here we have an activation layer, and the activation layer is basically adding nonlinearities. And in nutshell, I tend to believe the most interesting things all come from nonlinearities. So it's very important to learn a lot of very important and advanced features in your data to have this nonlinearity components. Now there is a more interesting layer here that is more relevant for the processing of images, and really that is the layer that really define the new transition into AI as we know it today, all the ability to process a large amount of images mostly come from this type of convolutions, where the actual kernel, because we saw the kernel before, that is basically the matrix here that multiplies the inputs, is instead applied to a small area. You see? Yeah. And that kernel is multiplied across the area all across the original image. So you have here a kernel, you have your original image, but you are separating different components of it. And you are generating, you see, the products, but only for small areas. This are generating what is called an activation mode. Now, this process brings several advantages. I mean, certainly, this is a lot smaller. And the fact that, you see, these parameters W, X, Y, Z, whatever they are, of the matrix, are equally applied all across the image. It means I have much less parameters than if I had a kernel the same size of the image. There is not going to be 4x4 like here. It's gonna be a lot larger, at least. I mean, if you have a small one, maybe 30x30, that will be a very big kernel, but a normal kernel in a convolution could be 2x2, just like here. Very small in terms of parameters. And this is also the reason you can use GPUs, because you can do this multiplication many times in parallel processes in GPUs or GPUs, the graphical processors. They allowed you to do a lot of parallelization of simpler processes. So you do have to use things like parameter sharing. That means parameter sharing is that concept exactly of using the same kernel all across the image as it moved across the image with exactly the same values of parameters, assuming that the image is equal. And not only is great for GPUs, but it models the behavior of the human eye, where the cells in your eyes are processing data in a way, I mean, every single cell, living cell capturing that light is just identical. It doesn't matter if it is at the very center of the eye or is of the reception area, or it is at the edges of it. It just captures light exactly the same way. And this works about the same way as this convolution process. There is another less machine learning oriented layer, but it's also very important in this multi-layer processing systems, which is the max pooling layer. Would go and just take an area and choose the maximum value, and the reason is usually that maximum value is the one that gives you some information, and the other ones may be close to zero, not too relevant. And well, based on that assumption, this layer also move across the image, similar to the convolution, but without doing any AI. It doesn't have any learning parameters, just chooses the maximum value. And the pooling layers are that relatively simple step. So now let's look, I mean, also, thanks to the fact that a lot of people have developed very powerful libraries like TensorFlow. There's also a PyTorch one I'm not showing here today, but these libraries have all these implementations, all these layers. You can simply implement them as a kind of a Lego. You do have to understand some of the parameters that I have been talking about. And here, for example, we use Python to just import TensorFlow. Well, here I use Python to import a sequential class, and that class is gonna basically just arrange the layers in a sequential form, one after the other. Then we have a series of layers: convolution, max pooling, max pooling, upscaling layer. So max pooling kind of contracts information by just selecting the largest value. The upscaling layer kind of expands by just repeating many times the value. We'll see the details. A flattened layer that just takes everything and put into a line, into a vector. It could be a whole dimensional matrix, but it puts that into a vector. And then the dense layer, also we talk about that. Now, here we add a convolution layer. I'm not going to talk too much about the details, but this is about kernel size, how many times I do that multiplication, non-linearity, the non-linear activation. The padding process is basically just maybe adding extra sizes to make sure the image is not contracted in the processing, in the convolution. And you have an input tape, which is the original image. You do max pooling, you do convolution, and don't worry about if there is one or two details about this that you're not understanding. This is a first class. Max pooling layer. Again, you generate here. This is my feature vector. What is this? This is this, my bottleneck. And then we have the decoder. The decoder expands the data back using a dense layer, sorry, then reshapes, and that's upscaling of the image, trying to bring it back to an image. Remember that we contract the image, we expand it again in the decoder. So this is the decoder component. And we have, again, a convolution here. The result is we encoded, we generated a feature vector, we decoded the data. So there we have how simple it is just to create this type of solutions. So let's talk also about the unit architecture. The unit architecture is a type of encoder, decoder architecture. It was originally developed for medicine, like, medical images that physicians have, and they want to detect the presence of a certain disease. But not only what that disease is, also where it is located. Is it moving here or there? And if you think about that problem, like where the location of certain things is, it looks quite similar to this. I want to see where the fuzzies are and how far they go. So that looks similar to the problem that physicians have of identifying the location of diseases within a medical image. So it has an encoding layer. It does have something interesting, which is basically in the processing of the image. It sends some information with less processing back to the output, faster to the output, and having these skip connections. And that skip connections would be something like in some steps here of decoding, I would just take the input, the knowledge that I have, and send it here to the output. It will still do the bottleneck and so on, but somehow the output will have more information that is less processed about the original image. And somehow that unit architecture keeps more context information by doing that, by keeping that skip connections. Now, this has been very successful in the processing of medical images, and it has been used also for modeling things like seismic classification, for phases classification, and there is some researchers that have also changed some of the components. So this is quite large, involving many convolutions all through the processing and also in the coding component. So if I just write down the shape of that, there wouldn't be a space in the whole slide. So this is why I show this very simple example that probably is not going to solve much of a problem, but whenever you have something like a big solution like this, you will have just simply many layers, just a lot more than I have here, to build an architecture of this type. Now, you generally don't have to go through those details. That architecture, you usually just begin from something that has already been developed. You don't have to develop anything from the scratch. So you learn from what other people have done if you are just applying your solution. So we're already at 12, 16. That's more than 45 minutes, Nick. So